This is the first lecture for Math 302, which is ordinary differential equations. I want to mention right at the start what the organization of the class is. This class is being offered in a summer semester. Sometimes they're very short, like 5.5 weeks. Sometimes they're a little longer, which is 10 weeks, but overall they're very short. The official textbook for the course, which you have, goes through various topics and then revisits them and goes back and forth in discussion, sort of a discussion mode. I wrote these notes so that all the topics are in one place and there isn't that discussion mode. It's more of an outline mode. I did this because I'm pretty sure that that's going to help us get through all of the material for the test in the short summer session, and also it's good for reference. I'm going to follow the order given in the lecture note. On Blackboard there's two ways to get at the lecture notes. In one case you can download an entire zip file for each chapter and then unzip it and either print it or look at it on your computer whenever you feel like. The other way to get at the lecture notes is that each one of them is listed separately on Blackboard, and you can look at them on Blackboard by clicking on those links. You get the same lecture notes both ways. Now the titles of the lecture notes give the order of the class. So they start off with CH, some chapter number, then some lecture number, which we'll call YY, and a title. There are 3 chapters in the lecture notes. Chapter 1 pretty much correlates with chapter 1 in the text. It's first order equations. Chapter 2 is second order linear and then planar systems. And chapter 3 is nonlinear. Also forcing is in here, so chapter 1 correlates with the text. Chapter 2 and 3 are just my organization, and here's how it is. Chapter 3 is second order differential equations and planar systems, as well as the topic of forcing. Chapter 3 is nonlinear. The lectures go in order. Chapter 1, they go from 1 to 12. Okay, and then there's a title that gives you an idea of what's in the lecture notes, but instead of writing a paragraph describing what's in the notes, I'm using the table of contents. So each lecture note starts with a table of contents that gives you the topics that are covered there. These notes are in PDF format, but the table of contents is not clickable. These are not links. You have to go to page 8 or go to page 11. For each chapter there's a homework file on Blackboard, and the homework file gives references to the text, some pages to the text for each topic, and then it gives suggested homework problems out of the text. Because of the length of summer session, at least this summer session, the homework won't be corrected. In the future that might change. So the question is, what is a differential equation? There's no really good set answer. Basically a differential equation is it's an equation, so it contains an equal sign, and it contains the function and its derivatives without the function being specified. For example, it might have the second derivative of some function, y, y of t is a function, and it's not specified, but it's listed here and it's listed over here in terms of its derivative. This is a differential equation. The goal is to find y, or the behavior of y. The ultimate goal is this first one here. It's to find a closed form solution. A closed form solution is one in which the solution is written as some combination of the elementary functions of algebra and trig. So it could be polynomials, sines, cosine, tangent, hyperbolics are okay, and of course exponentials, for example. That's a closed form solution. In order to get it, you need analytic methods, and we have some of those discussed in this class. However, sometimes no analytic method exists for a particular differential equation, especially the nonlinear ones. Or even if the method exists, it might contain integrals that are impossible to evaluate. In that case, you do not have a closed form solution, but you still have to, in a sense, deal with the problem because the differential equation may represent a physical system that you're trying to build. So the next step is to move to what are called numerical methods. The direction fields are part of both closed form solution and numerical methods. They're just another look at the differential equation, but in a sense they are a numerical method. So in numerical methods, you use various methods that have been developed to start the differential equation at a certain point and draw the graph of the solution. So even though you can't write it, you might start it here and be able to draw how it varies with time. So this would be y, as sorry for my drawing. You'll notice in these lecture notes that I wrote and in this work that I have absolutely no artistic talent at all. So apologize for the unpleasantness of my drawings, but I hope they're informative. Okay, so this is a second method, and it's a numerical method, and there's many of these. We're going to discuss 2 of them in this class, but in the future you will be taking additional classes in numerical methods themselves. And in that case, you will learn the numerical methods that are used in industry, in research, in electronics industry, and in kind of physics experiments. You'll learn about those methods. They're much more advanced than the ones that we're doing here. These are just an introduction to them. You also have to work through the how robust the method is, the stability, and the errors of the method, because this is error prone. What if you do a numerical method and you sort of trace it out here, but the actual solution does something like this? Who knows? Maybe you just got off on the wrong track. How do you account for that? Those are things that you have to study in these advanced courses. These numerical methods and differential equations are an entire career path in physics, engineering, and in mathematics, because mathematicians work in industry. I'm saying industry in general. Okay, and numerically solving a differential equation, especially in the complicated geometry, is a big part. There's a lot of work in this area, and there's one field that's especially interesting: computational fluid dynamics. I hope that some of you get interested in that field. It's very good, and just wanted to mention that. Okay, now we're going to move on to a third aspect of differential equations, and that's called the dynamical system. Dynamical systems, or dynamical behavior, studies just the behavior of the solution curve. Sometimes it gets at the solution curves, sometimes it doesn't quite get at the solution curves. But it studies this behavior over different circumstances. And in this course, you'll see the phase lines, phase portrait, subject, that's part of it. Another part is bifurcation, which shows how the differential equation, how the solutions might move through different behaviors as parameters in them change. In the past, dynamical systems was studied as a separate course called dynamical systems. There probably still are advanced dynamical systems there, but now a lot of the dynamical systems is brought into ordinary differential equations. If you took this course a couple years ago, all you got was the dynamical systems, or the ordinary differential equations part of it. You got this. And you studied many more analytic methods, and you studied them in more detail. Now, the idea is that because of the use of computers, people do not spend a lot of time studying analytic methods, and dynamical behaviors are important, so they are brought in to this class, and the emphasis on the analytic methods has decreased. Use of computers is a big question. Working through different analytic methods develops the brain, and so in and of itself it's important. But there are many crossovers between using computers and solving equations, so that's how things are done now. When you look through your text and you see those really interesting looking graphs with lots of curves on them and circles and that sort of thing, that's part of the dynamical behavior part of this course. So here's just a summary of what I said before. So this class will cover the analytic methods that will yield closed form or special solutions for certain types of differential equations, give an introduction to numerical methods, and discuss dynamical systems also. Here's a listing of the basic classifications of differential equations. It's important to know these because the method of solution differs between these different classifications, and also the type of expected solution differs. There are also theorems of existence and uniqueness and theorems concerning linearity that apply to different equations depending on their classification. The first classification is ordinary versus partial. The ordinary differential equations are the ones studied in this class. In an ordinary differential equation, there is only one independent variable. Usually, almost always, in this class and in the textbook, it's called t. It doesn't have to be t in a real world situation, but a lot of them are time dependent. So we just use t for this case, and that's the ordinary differential equation that are studied in this class. Partial differential equations, or PDEs, those equations have more than one independent variable. Here's a nice wave equation, and you have here three spatial variables, x, y, z, and time, t. And you also notice these are partial derivatives. You'll study those in a different class. The next category for a differential equation is its order. The order is the value, the number of the highest derivative in the differential equation. We're only working with ordinary differential equations, so all you look for is the highest derivative here. This equation is of second order. This equation is first order. Chapter 1 is mainly first order equations. Chapter 2 is second order equations. Linear versus nonlinear. This is a big topic. It really separates a lot of methods, it separates theorems, and it's very important to be able to identify whether the differential equation is linear or nonlinear. However, the definition of a linear differential equation is a little tricky. For a linear differential equation, the function and its derivatives appear only to the first power. They aren't multiplied, they're not in square roots, they're not the arguments of a cosine, they're not up in an exponential. So in this case, it looks just like this. Here is the derivative, first power. Here is the function to the first power, and there's just a constant k multiplying it. Okay, this is a linear differential equation. And we look at this next one. This is also a linear differential equation. The terms that are multiplying it, I'll highlight them. And the one that's over here that doesn't have anything to do with y, those are highly nonlinear. A sine, an exponential, and a polynomial. But the equation is still considered linear because the second derivative is not squared, cubed, multiplied. It's just sitting there by itself. The first derivative and the function are the same. They're to the first power only. This is a linear differential equation. This is a linear differential equation. Here is a nonlinear differential equation. Okay, what's a catenary? A catenary, if you had a cable and you took two poles and you strung this cable between the poles, the catenary is the shape that that cable will assume if the only thing acting on it is gravity. And here's the equation that describes that. G is gravity right here. Okay, rho, get some tension T. Okay, so this is nonlinear because here's the first derivative. It's not only squared, it appears under a square root sign. So just to say this again because it'll come up later, in a linear differential equation, the function and its derivatives appear to the first power only. Other terms that might involve the independent variable can be as nonlinear as they want to be. Autonomous and non-autonomous have to do with the independent variable. If the independent variable does not appear anywhere in your problem, except this meaning y is a function of time, then that's autonomous. If t, in this case usually, the independent variable is sitting here by itself, here 4t plus 6, or sine omega t, then that's a non-autonomous system. And the last distinction we have, or last characteristic of a differential equation, is whether it is homogeneous or non-homogeneous. If it's homogeneous, then if you put all of the terms involving the derivatives of y, however many there are, and the function itself on one side of the equal sign, all you have on the other side is 0. That's homogeneous. It all equals 0. There is no term that doesn't involve y or its derivatives. For non-homogeneous, you will have a term out here. It's usually called the forcing function. Okay, so this is a big difference. When we get to the theorems of linearity, the principles of linearity in the next lecture, you will see how they apply very differently to homogeneous equations and non-homogeneous equations. To really specify a differential equation, you don't just write the equation by itself. You have to write what are called either initial or boundary conditions. Here's the reason for this. When you take a derivative, as you know from calculus, if I have some function, say y t is sine j. I take a derivative, okay, that's fine. I get 2t and I get a 4, but I have lost all the information about the 6. I'm going to take another derivative. At this point, I've lost the information about the 4t and the minus 6, both. If I take a third derivative, now I've lost all the information about that polynomial. So taking derivatives results in loss of information. When you integrate, say if you started here and integrated, you would end up with the constants of integration. And those constants of integration form a family of possible solutions. So I'll draw what it might look like if you had something simpler than that example. So here's t, here's y of t, and if I have a very simple equation, say I end up with y of t equals t squared plus some constant c. This just came from undoing a single derivative. Well, then depending on the value of c, I'll have different parabolas. If c is 0, I'll get something like this. C is, say, 4, I get something like that. Oh, that's supposed to not quite be like that. C is 5, I get something, minus 5 looks like that. In order to pick out which particular solution applies to your problem, you need a value for c. If c is 0 and you know it, then you're working on this curve right here. If c is minus 5, then you're working on this curve. So the value of c allows you to pick out the curve out of the family of curves. If you have a differential equation of order 3, then you will have a 3-parameter family of curves, and you will need 3 initial conditions. That's a test question, I think, on the final. Right? The number of derivatives dictates how many parameters you need in order to solve it. You'll need values for 3 constants, and the constants will occur. They won't just be hanging out there like C1 plus C2 plus C3. They will have various functions of time or whatever associated with them. So you have to do some algebra to work on that. But you will need 3. So if you have an nth order differential equation, you will have an n parameter family of solutions, and you will need n values in order to solve and pick out the particular solution that applies to your problem, to your situation. There are 2 ways that these values are given in differential equations. They're either given initially or at the boundary. They could be given different ways, but these is the traditional ways that they're given. So you have initial value problems or you have boundary value problems. So in an initial value problem, think of, you're looking at y as a function of time. And say your problem starts out at t equals 0. And this is the start of your experiment. This is when you throw the switch or something happens at time t equals 0. It doesn't matter what the time is. Usually we call it t naught, but you can translate back and call it t0 and just modify all your times. So we'll say it starts at t equals 0. Then for an initial value problem, you need the value of the function at t equals 0. If you have a higher order differential equation, then you also need the derivatives at t equals 0. These would be called the initial values. They're the values when you throw your switch, when you start your problem. So here is a second order differential equation. Second order because the highest derivative is 2. And here are the 2 initial conditions. Here's the first one. Y at 0 is some value y0, and the derivative at 0 is often called v0. If y is displacement, then its first derivative is velocity, so sometimes you'll see this as velocity, other times as y prime 0. It doesn't matter at this point that they have numbers or not, but they need to be specified like this, y naught and v naught or y prime naught. So I'm going to show you what to do with these initial conditions. Here is the general solution for this differential equation. It's just given here without derivation, and it has 2, C1 and C2. Here are the 2 constants it has, because if it's second order, you expect 2 constants. Remember the n parameter business, so second order would be a 2-parameter family, and here are your 2 parameters, C1 and C2. Here are your 2 initial conditions. Now you want to write the, whoops, this slide still has A and B on it. Okay, we'll just call them A and B. Okay, instead of C1 and C2, I used A and B on this slide. I think I did that in the written notes too. Doesn't matter what you call them, but there's 2 parameters, A and B, or C1 and C2. Now you want to rewrite those parameters, the A and B or C1 and C2, in terms of the initial condition. Let me explain how that's done. Okay, the first initial condition was the value of the function at 0. So you take your solution and you evaluate it at 0 and you make it equal to y naught. So if I put a 0 here and a 0 here, of course the sign terms are going to go away and all I get is A. So I know that A is equal to y naught. So when I write my solution, instead of writing the A or the C1 here, I replace it with y naught. That sounds kind of funny. Now for the second one, the second initial condition was the derivative of the function evaluated at 0. So I take the derivative of the solution, which would be a square root k over m sine square root of k over mt, but I replace the t by 0 because I'm evaluating at 0. Same for the second term. This one goes away and I end up with b root k over m is equal to the initial condition, which label as b naught. Could be y prime naught also. So I solve for b in terms of that initial condition and I substitute it in here. Okay, so why do I do this? Before, when I just had the A and B, or the C1 and the C2, I had no idea what they are. Now I can look right here and I can say, if I have a different initial condition, I'm just going to plug in new values for Y0 and V0 and be able to use the solution without doing any more algebra. This shows me where those initial conditions occur, how they occur in the solution. Y0 appeared by itself, one of the cosine term, but V0 is multiplied by the square root of m over k. Here's a second example. This is a first order differential equation. You see the first derivative is all you've got here, so it's a first order differential equation. Here is the initial condition, y at y0 equals y0. This is the solution. If you're given a solution and you want to find out if it really is a solution, what you do is you take its derivative, however many derivatives there are, and you plug the derivative and the function back into the solution and see if you get an equality. Okay, let me try to do that here. Here's the proposed solution. So I'm going to take its derivative. Okay. That's pretty easy. So I'm going to get, I can see a bunch of negative signs. Okay, that's the derivative. Now you can try to undo that and see if it equals yt times y, 1 minus yt, but you know how to work problems one end against the other. So I'll start the other way. So what is y of t times 1 minus y of t? Okay, so I've got, and then I have 1 minus, same thing. I'll use common denominator here, so I've got 1 over 1 plus c e to the minus t, and I will have 1 plus c e to the minus t minus 1 over 1 plus c e to the minus t. Here I've got my squared terms, the ones are gone, and I do get c e to the minus t over 1 plus c e to the minus t, which is indeed the first derivative of this function. So that's all it is. You just take the known derivatives, you take the function, you plug them back into the equation and see if you do get equality. Now let's write the parameter c. Remember, this is the first order differential equation. We have one parameter, and that's all we have to solve for, and we have one initial condition. So we want to get the c in terms of this initial condition. So I start here and I will evaluate the function at 0 because the initial condition is given at 0. And I know that's going to equal y0, and it will be 1 over 1 plus c e to the minus t, and e to the 0 is 1. I want to make a comment here about negative exponentials. Negative exponentials, e to the minus alpha t, e to the minus lambda t, whatever, should be left as negative. Do not write this as 1 over e to the lambda t. This is never done. The only time it's done is in some algebra classes. Some algebra teachers insist that every negative exponential be resolved. So if you have x to the minus 5, they always want you to write it as x to the 5. Okay, fine for algebra. Don't do that here. Why not? Because these are so important in physics, engineering, even if you're in biology, they're important because these are the decaying exponential. You need to see them as negative. This doesn't look like a decaying exponential to anybody. This does. Everybody recognizes that as a decaying exponential. They don't want that resolved into some 1 over some positive exponent. And that is just a leftover from algebra practices that are not universally done. So that's the comment I wanted to make there. So I had to erase the entire screen because of that comment. Okay, whoops. Y at 0 equals y0 plus, which is equal to 1 over 1 plus, see what happens when you go to ranting. Okay, here we've got y of 0 equals y naught, 1 over 1 plus c. So all I do is solve for c. C equals something, 1 over y naught minus 1. Okay, which is kind of painful there looking, isn't it? Okay, I could write that as 1 minus y naught over y naught. So now when I write my differential equation, I don't write c anymore, I write this thing, which actually, I don't know, I do something else with it, but here you go. When I said before, don't put things in the denominator, if the negative exponent occurs in the denominator, as it does in this logistics function, then you leave it there. It has meaning. So just don't go through all that work to resolve negative exponents. So here's an example of what we did here was we verified that this was the solution of this differential equation. Then we took the one parameter here. We only have one parameter, c, because we have a first order differential equation. We have one initial condition. We rewrote the parameter in terms of that initial condition, and this is the result. I'm going to say here for a minute what boundary value problems are for your education. We are not going to study boundary value problems in this class. Here's the idea. Okay, I'll use that square thing. Say you were, these occur more in partial differential equations. Say you were looking at the heat distribution in a piece of metal. If you're going to specify the initial conditions, you would start here at the beginning of this piece of metal, and you would specify the temperature, and you'd have to specify actually a couple, well, let's just specify one derivative. Let's just leave it like that. And you'd specify that at the beginning. That would be an initial value problem. Okay. For the boundary value problem, you can see this is sort of awkward. What is the rate of change of the temperature? Boundary value problem, you would give the temperature here, and maybe this is the other end of it, at, say 1. You would give the temperature at the boundaries, at the edges of the problem. If you needed 2 initial conditions, this would give you 2, this would give you 2. This is considered a boundary value problem. Some of the theorems for existence or uniqueness are not the same for initial value and boundary value problems, and we're not going to study them in this class. The last topic I want to cover in this lecture are those additional notes that I wrote in there and some other comments, and this is for your education. The book itself is very casual speaking. I think there are 2 educational philosophies now, at least 2, and one of them is that you should approach the students where they are with the lowest level of vernacular speech, and you should not in any way scare them or challenge them, and then you get them in the door and hopefully they learn something. Okay, so you sort of go down to the level of where you think the students are, which is okay, a judgment call. And that's sort of where these modern textbooks are written. However, there's another way of looking at things, and it's sort of mine. I guess I'm sort of a dinosaur. I am a dinosaur. You give the students the highest level because you know they're capable of it, and you pull them up to that highest level that you can, and then after you do that, you hope that they go on and make progress. So that's sort of my philosophy here. But now let's talk about the language issue. That textbook got away with that language issue because of the educational philosophy. However, if you were to stay in academics and you were to write an academic paper and you submitted an academic paper in the language given in the textbook, it would be rejected by the reviewers and by the editor. You wouldn't even get by the editor. He wouldn't even send it to a reviewer. Every single word in there has to be correct, and it has to be done in the proper format of mathematics, physics, engineering, which are all the same. Very precise, very specific languages. Okay. Also, if you're doing this numerical calculation in industry, you must start your main routine of your computer program, your main subroutine or your main routine, with a very detailed specification of every variable you're using, the type that the variable is, and everything about the problem. There's 2 reasons for doing it. First, it's required. Second, if you write the computer program and you don't write that kind of header, 6 months you're going to come back and look at that computer program, and you will have to reconstruct what you did. And it's a very painful and long process. So this sort of welcoming language is okay in this one philosophy of education, but it is not good in any form of actual work. It also has another implication, and that's financial. I'm going to point out two big problems, and this one is on the midterm, I think. What about the Hubble telescope? The Hubble telescope was this big deep space telescope. It was decades in planning, in really getting the specifications down and designing it and getting the funding and getting the teams together to work on it. And it cost about $2 billion a while ago, so it was a lot of money to build it. Then it was deployed in space and found that it took some pictures, but not the real pictures for which it was designed, for which it was built, for which all this money was put into it. In other words, it was failed. Okay? A very smart person figured out what was wrong. They were able to correct it. That cost billions more. And now, what was the cause? There's been a lot of analysis as to what the cause was. Here's the deal. There was a subcontractor sent in some numbers, calculations, as the result of calculations, sent them in to NASA in order to be used in design and building something. We won't mention the subcontractor's name, so we don't shame them. Anyway, they sent these numbers into NASA, and when they sent the numbers in, they didn't put any values with them. They sent the numbers 5, 12, 6 to the minus 9, something like that. Okay, they sent those into NASA. I don't know the exact numbers. NASA accepted them without the units. When the whole project starts, it was specified that all units would be given in SI units. The subcontractor happened to do the system in British units. There's nothing wrong with British units. They're perfectly fine. People always disparage British units because they say it's more modern to have things based on 10. But that's not actually true. British units are based on 12. And 12 is one of the better numbers in the world. It's only second to the number 60, as used by the Babylonians, who were, I guess, a lot smarter than us. Why are these such good numbers? Look what you can divide them by easily. Just about every number. So maybe 7, 9, 11. Look what you can divide them by. 3, 2, 3, 4. 60 you can also divide by 5. You can divide by 6. Okay, 7 and 9 are out. 8's out too, isn't it? Okay, 10, 12, 15. These are very, very good numbers, and there's nothing wrong with the British system. What was wrong was a lack of units. That is the casual speaking, the incorrect specification of the problem. And because of it, it cost billions of dollars, and it's only by the genius of someone who was able to figure out what was wrong and correct it, and also a whole bunch more money had to be put into it. So it was a very important error. All right. Another one is the Hubble or the Apollo rocket disaster. One of those was done early on in the program, and when computer programs were starting to be used instead of more hand calculations, big computer codes. And this one was written in Fortran. Fortran requires that any angles be in radians. So if you go sine 45, the 45 to you is in degrees. To the computer program, it's 45 radians. And that's what happened. Units weren't specified. So I'm giving two examples when units aren't specified, but other things can also be an issue. So this is the conclusion that I put in the written lectures. Casual speaking might seem welcoming to humanities majors and others. It has no place in mathematics, physics, or engineering. I'm going to give you a second look now at the on those additional notes for engineering and physics. Also, you might say, I'm just going into math, and so I don't need to know these things. But the question is, what are you going to do with math? If you're going to teach algebra, you don't need to know this. But if you're going to make a living, well, you can make a living teaching algebra, but if you're going to make a living doing anything else with math, you do need to know standard practices. Providing computational support in engineering and in physics is a very good job for mathematicians. and you need to know how to work with those people and how to do this kind of problems. So I'm going to point out a fallacy in math books. Math books set up a problem, for example, a circuit equation or a heat conduction problem or anything they're trying to work with, and they set it up and then they immediately go and give it some values. For example, here is a solution, a problem for trying to find the voltage on a capacitor in a series RLC circuit. So they set up the equations and then they give these values. Here's some values which may be reasonable in a certain situation, and then they solve it with specific values, and here's the solution they get from it. Okay, the solution is essentially useless. First of all, I don't know if this is even a decent value, or if this the frequency here of the cosine term, is that even decent given these? I can't trace it. Also, if someone comes along and tells you that, oh, they gave you the wrong numbers, it should have been a capacitance of 0.25 microfarads instead of 0.2. What do you have to do? You have to resolve the entire problem, and every time you're solving it, you're making more and more numerical errors, or you're having more and more opportunities for making numerical errors, and so how do you know the next solution is even right either? A much better way, and the way that I will do it in this class, and if and when there's homework for this class, you'll be required to do it this way too, is to solve it using variables. Don't put the numbers in until you're done. So you end up with something that looks like this. Initially, it looks a little more formidable. Look at all these terms in here. I don't know, maybe it seems overwhelming, but that's fine. It has a benefit. Once you have solved like this and people give you a set of numbers, you just evaluate it. If they give you a different set of numbers, you evaluate that again. You can take this expression and code it into a computer or code it into your calculator and then just evaluate it. Okay, so it has great benefit for saving you time and saving you potential errors. The second thing is, in terms of the errors, if you write your steps one above the other, you can watch how the resistance moves through this calculation. And you can kind of reaffirm that you have done it correctly. Also, if you know kind of what you expect, you can say, oh, these terms look right. When I wrote these in the lecture notes, I didn't have the right brackets around 2L, and I ended up with something that looked like this. Because when I set the equation, I forgot to put brackets here and the L escaped and went out here. I can immediately saw, oh, when I looked at it here actually, that it was wrong, and I can make that correction. So it helps you. If I had done this wrong up here, I would never have been able to find that error. So the next thing that when you do this for work is that most people want to do parameter studies. They want to say, well, let's go through all kinds of values of inductance, resistance, and capacitance. You need the parameters visible in order to do that. And the next benefit, and very big benefit, of solving with variables is then you can identify what's really going on in the circuit. What kind of equation is this? First of all, okay, let me draw the equation, or draw the solution here. All right. This is a damped sinusoidal wave. Okay, with t equals 0, the cosine is going to be 1, and this exponential will be 1. So it's going to start at 1, and it's going to ring, it's going to oscillate, but it's going to be modified or multiplied by this decaying exponential. So it's going to go something like this. And here is that decaying exponential, multiplying the cosine so that you don't go back up between plus and minus 1. Often this is written down here just to create an envelope. So here's your decaying exponential, and here's your cosine term multiplied by the decaying exponential. And you can see right here what the attenuation is. The attenuation is R over 2L, over 2L. So if you increase inductance, you decrease the attenuation. If you increase R, you increase the attenuation. So you can see that by this form right here. So this gives you an understanding of what parameters are involved in attenuation. This term here is the frequency of the cosine. You can see how if R is 0, you just have the cosine of the square root of 1 over LC times T, and this is your resonant frequency. So all sort of information is obtained by solving with variables.